Good evening, everyone. Welcome to the homework portal. This is week number 7, or whatever you call it, as the one problem per day. Okay, so this week's theme will be focusing more on quantum mechanics, then atomic physics, nuclear physics, fission and fusion reactions. Okay, so every week we will have a theme. For IB1, I have had something like electricity problems. You can also refer to the problems in electricity, electrostatics, magnetism, which I am doing it for them. Okay, and for here I am doing it for these 3 chapters. So if IB2 students can do both of them, it will be very useful for you. You will be doing a better revision. Okay, so if you keep on doing one problem per day, which means I'm doing one for IB1, one for IB2, I think it's more than sufficient. You can easily do all the problems together. Okay, let us begin before wasting our time. And this problem is for 13 minutes, and let us start with this. Okay, so now first thing, outline by reference to the start the timer, right? Outlined by reference to the nuclear binding energy, why the mass of a nucleus is less than the sum of the masses of its constituent nucleus. Mass of a nucleus is less than mass of the constituent nucleus. Okay, why is it so? Okay, mass of protons plus mass of neutrons is what is the question over here. The reason is because, see, when you want to bring 2 protons or 2 nucleons, whatever you want to bring it, to close, to bring this and make a complete nucleus over here, you need to supply some energy. And we know when energy is supplied, energy is converted into mass. By which equation? E is equal to mc squared. That means when you provide energy, that means some amount of mass is now given to it. Okay, it is like a coating, for example. Okay, so therefore the sum of these 2 masses, let's say m1 and m2, okay, while you do this fusion reaction, will no more be m1 plus m2, but it will be m1 plus m2 plus some delta m, let us say. And after binding them, the total mass of this nucleus is just capital M over here. So as a result of this, there will be a difference in the mass. This mass will not be equal to this. This will be more than that. So what is that you require? You need to write. Your first point, you should write this for 2 marks over here. You should write this as energy is released when nucleons are brought together. This is the first thing that we need to write. And secondly, so a nucleus is being formed. And secondly, you can say energy is required to bind the nucleus. Okay, that's what we already mentioned. So therefore, masses of this one will be much larger than the mass of the nucleons. This is what you need to mention here. Okay, now let us move on to the next question. Polonium 210 decays by an alpha emission into lead 206. Okay, so polonium 210 leads, write the equation, it becomes more easy. Decays by an alpha emission to make as lead is what? Pb 206. Okay, fine. And then the following data is available to then okay. The calculated MeV, the energy released in this decay. What is the energy released in this decay? So what should I do? So according to the previous problem, we already said that first let us take up these 2 masses. Add these 2. Okay, I am not considering this one. There is a full mass of it. I am just considering these 2. When I do this, add this, what will you get? 5 plus 1 is 6. 4 plus 5 is 9. 9 plus 1 is 10. 1 carry here. This is 2. 2 plus 1, 3. 3 here. And this is just 9 over here. And this is 205 plus 4 is 209. So this is nothing but your total mass of the constituents. And this is your mass of the complete nucleus. Now let me subtract one from the other. Right? So delta M, which is you get as a mass defect, which would be 209.93676 U minus 209.93096 U. When I do this, what is the answer you get? U here, 6 minus 6, 0, 17 minus 9. 17 minus 9 should be 8, right? 9 plus 8 is 17. Here 5 here, and here it is 0. 0, 0, 0, 0, 0 here. Okay, so you get 0.0058 U over here. Now since we have got delta M over here, I need to get the binding energy, which is nothing but delta M into C square, which will be equal to how much? 0.0058 into UC square. I'm not going to substitute all of them and get the answer. The reason behind is because I need the answer in terms of MeV. So what I'll do, there's a shortcut. What is the shortcut? We know that 0.0058. We know that 1 UC square is equal to 931.5 MeV. MeV, right? This timer, I'll just pull it across and put it at the top. Okay, 931.5 MeV. So I am going to just write this one here like this. 931.5 MeV. When I do this, let me do the calculation so that I get the final answer. So I get 0.0058 multiplied by 931.5 will give you 5.4. What is this now? 5.4 MeV is the amount of energy required to, amount of energy released in this decay. Okay, so therefore polonium, when it gives rise to lead, then this is the amount of energy which is being given out. Okay, the polonium nucleus was stationary before the decay. Okay, so this is your polonium nucleus which was stationary. Then what happened? Decay happened. When decay happened, what happened? So this gave rise to lead plus 2He4 alpha here. It gives something like this, right? Show by reference to the momentum of the particles. Now, see, is the momentum conserved here? Momentum is definitely conserved. No external force is acting on it, right? So why did this happen? Because it's an internal force. This polonium became unstable, so it started to break out, right? So therefore, this is because of internal force. Momentum is perfectly conserved. Okay, so COM can be applied. Okay, then kinetic energy of the alpha particle is much greater than the kinetic energy of the kinetic energy of the lead nucleus. So if I say COM is conserved, what is the equation I can arrive at it? I can say first mark will go for, we can say, since no internal force, no external force was applied, and the decay happened only due to the internal force, conservation of momentum can be applied. That gives 1 mark. Okay, so that statement gives you 1 mark. Then the second statement, what should we write? We should now write applying COM. Okay, what do I get here? Momentum of the polonium nucleus is 0. Okay, before explosion. This is nothing but an explosion example. In conservation of momentum, you have to learn something like you have a bomb and this bomb exploded. As a result of it, mass M went to this side and mass M2 went other side, and you applied that one, right? The same thing is applied over here also. Okay, so then this should be momentum of this plus momentum of alpha, momentum of the lead plus momentum of alpha, which means PB is equal to minus P alpha. This is what we have. Okay, now what we do is, we know we'll take kinetic energy alpha divided by kinetic energy of lead. Why do I do it? Because I need to compare them, right? So we know that kinetic energy is given by half mv square. Okay, m alpha v alpha square divided by half mpb multiplied by vpb square. But I can also write this as p alpha square by 2m alpha divided by p mbpb lead square divided by 2mpb, right? Now we know that ppb is equal to minus p alpha. So therefore these two are equal, because when I square this negative goes away, right? So these two goes away. So what is the answer here? I get this as, this 2 and 2 also goes away here, right? So therefore I get this as mpb divided by m alpha. What is mpb? Lead, right? Okay, so therefore this mpb is larger than m alpha. Okay, so lead, what is the mass of lead? Mass of lead. How many nucleons it has? It has around 206 nucleons, and this has only 4 nucleons. So I can just say this is equal to something like 206 divided by 4, right? So therefore this is definitely greater than 1. So if this is greater than 1, then definitely you can say Ke alpha is greater than Ke lead over here, which is as per required. Okay, let us move on to the next one. In the decay of polonium, the alpha emissions can be accompanied by the emission of gamma photons. Okay, the same, all of same wavelength, 1.5 meter in power minus 12 meters. Discuss means what? You at least need to write 3 points. How this observation provides evidence for the discrete nuclear energy levels. You need to show how this is equal to discrete energy levels. What is a gamma photon? So first you write down gamma photon is emitted only when a nucleus transits or jumps from excited to ground state or any other excited state. So therefore there is a gamma photon emitted. Okay, so this gives you the evidence for gamma photon. Then second point, because we need 3 points, right? All are of the same wavelength. Okay, same wavelength implies same frequency, and then the energy of a gamma photon FHF is equal to delta E, which means when F is constant, H is constant, delta E is also constant, which means what? There is a constant different energy levels. Okay, the energy levels are not continuous. There is a discreteness. There is a discreteness over here, right? There is a discreteness. Okay, so we have put across two observations over here. The first one is, this is first 1 mark over here for this one. This will be for 1 mark. Okay, and finally your conclusion will be for 1 mark. Thus we have mentioned all the 3 points over here. Okay, let us move on to the next one. Next, a sample contains 5 grams of polonium-210. Polonium-210, you have 5 grams. Decay constant of polonium lambda is given to you is this is your lambda value. Lead-206 is stable. Calculate the mass of lead-206 present in the sample after 1 year. After 1 year, what is it remaining? Now first what we do is, let me assume something like this. If you have this much amount of, if M is the mass of polonium, let me say N0 is the number of atoms of polonium. This is guaranteed, this is evidenced over here, right? Now if M dash is the mass of polonium after 1 year, then N is nothing but the number of nucleons present in the sample, right? So therefore now what I can do is, we know that N is given by N0 e to the power of minus lambda t. Okay, so therefore now let us find out what's the value of N. So I will keep this aside. I will write N is equal to N0. What is the value of N0? I do not know. I will just substitute N0 only. E to the power of minus lambda minus 5.8 into 10 to the power of minus 8 into t. What is t? 1 year, right? It's asked here 1 year here. 1 year should be 365 multiplied by 24 multiplied by 86,400 seconds. For 1 hour you have for 1 hour, sorry, let me, not 86,400, this is 3,600 seconds, right? 60 into 60. Okay, so when I do this, I will get how much? Let me calculate this so that I get a clarity on what we are doing over here. So I get this value as 5.8. What is it? 5.8 grams, right? 5.8 grams. See, we missed it over here. Sorry, this is no. 5.8 is 10 power minus 8 is correct. Okay, so therefore 5.8. Just a minute, I made a mistake. 5.8 into 5.8 into 365 multiplied by 24 multiplied by 3600. So I get this as 182908 something you get. Divide this by 10 power minus 8. So how much is it? You see this is 1, 2, 3, 4, 5, 6, 7, 8, which will be 1.83. So I will write this as N0 e to the power of minus 1.83. Okay, is what I got. Now what I will do is, let me find out what is this value. Okay, 10 power minus 8 I have removed. So 1.83. So e to the power of 1 is so much. Oh my god. Now I'll do one thing. I'll write 1.83 minus, or first find out e power 1 by 1.83. If I do this, e to the power of, okay, I have to do it like this, e to the power of x power y to the power of minus 1.83. I get this as 0.887, 0.888. Okay, so I get this as N0 into 0.8. I get this value. Now, if M is proportional to N0, okay, then M dash will also be proportional to N over here. This is N over here, right? So therefore, I can now say M dash probably is equal to 0.8 grams over here. M is equal to M dash equal to 0.8 grams. Now, what is this actually? This is the number of, what is this? Polonium, not number, mass of polonium nucleus remaining after 1 year. The mass of polonium nucleus remaining after 1 year. Now, how much has got decayed? How much lead has been formed? Now, what is the question here? See, calculate the mass of lead. Okay, I don't want how much has been converted. Okay, so I want to see how much lead is been present. See, initially at t equal to 0, when the reaction started, there was no lead. Okay, but as time proceeded, lead started accumulating, while the polonium started decreasing. Okay, so therefore the amount of lead after 1 year is equal to 5 grams minus 0.8. What is 5 grams? Number of polonium, mass of the polonium minus whatever is left over. Okay, so how much is it? This is 4.2 grams. Okay, so now we have seen amount of lead. Is this amount of lead? No, it's not amount of lead. It is amount of lead plus alpha particle, which is left after 1 year is 4.2 grams. But actually we need only lead, which means what? I should minus that alpha particle mass also. Now, how do I minus that? That's the next question. So towards it, what mass of is lead only. I don't want this alpha. Okay, so which means I should subtract this value, but I am not able to get the value of u over here, right? See, I can only say mass of an alpha particle is just 4u, and why don't we subtract over here? But in this sample, how do you do? Because you initially had 5 grams of it. How many alpha particles were there? Quite difficult, but there is one more easier method to do. The easier method is like this. What we will do is mass of something like mass of lead nucleons divided by mass of lead plus alpha is equal to, how much is the mass of lead? Mass of lead is nothing but 206 nucleons, right? Okay, which you already know, 206 u divided by mass of lead plus alpha is equal to how much? Which is nothing but 210 u, which you already know. Okay, so this is theoretically so therefore now practically we already found out what is this, right? So therefore this u and this u goes away. We have this. So mass of the lead nucleus is equal to 206 divided by 210 into mass of lead plus alpha. Where is this factor? This factor is here. Mass of lead plus alpha after 1 year is equal to so much. So what I will do is I will substitute this one here. I'll write this as 206 divided by 210 into, how much is it? 4.2 grams. 4.2 grams. If I do this value, how much do I get? I get this value as 206 divided by 210 is equal to so much multiplied by 4.2. I get this 4.12 or 4.1 grams. This 4.1 gram is the right answer for the mass of the lead which has been formed. If you just write until here and do not include this one here, this below calculation, you lose 1 mark over here. Okay, so therefore see to it that you write it correctly. This was 3 marks. Okay, so we'll stop here. Let us see in the next video. Thank you.